resistant species. A planet, the end-Permian mystery. Did cosmic rays cause Earth's worst die-off? History suggests that mass extinctions favor organisms with specific adaptations. But the most devastating die-off our planet ever experienced contains an astronomical mystery. What if the Great Dying that wiped out nearly all life 252 million years ago wasn't triggered by forces on Earth, but by a cosmic catastrophe that left its fingerprints in ancient fossils? The end-Permian extinction stands as Earth's most catastrophic biological crisis. This event eliminated over 90% of marine species and approximately 70% of terrestrial vertebrates in a geological instant. For decades, scientists have attributed this mass extinction to massive volcanic eruptions from the Siberian traps, which pumped greenhouse gases into the atmosphere, triggering extreme climate change. However, this explanation comes with persistent puzzles that haven't been fully resolved. When researchers examine the end-Permian fossil record closely, they find extinction patterns that don't align perfectly with what we'd expect from volcanic activity alone. The traditional volcanic hypothesis struggles to account for the remarkable speed of the extinction and its highly selective nature. Some organisms vanished almost instantly across widely separated regions, while others with seemingly similar environmental requirements managed to survive. This selectivity hints at an additional mechanism at work, one that might have come from beyond our atmosphere. The fossil evidence contains unusual smoking guns pointing toward radiation damage. Plant spores from end-Permian sediments reveal widespread malformations across multiple continents. These deformities include fused pollen grains and abnormalities consistent with genetic damage from high-energy radiation. The global distribution pattern suggests a planet-wide radiation event rather than localized environmental stress. These malformed plant spores bear striking similarities to radiation damage observed in modern plants exposed to high levels of radiation. The specific types of fusion and developmental abnormalities match what we see in controlled laboratory settings where plants are deliberately exposed to radiation. Another critical piece of evidence comes from atmospheric signatures preserved in end-Permian rocks. Geological records indicate a sudden collapse of the ozone layer coinciding precisely with the extinction boundary. This atmospheric disruption would have exposed Earth's surface to dangerous levels of ultraviolet radiation, an effect that overlaps with what models predict would happen following a gamma-ray burst. The formation of specific nitrogen compounds found in these boundary layers aligns with the chemical reactions that would occur if gamma rays interacted with Earth's upper atmosphere. Research teams from the University of Kansas and NASA have proposed that these anomalies could be better explained by gamma-ray burst than by volcanic activity alone. Their models demonstrate how a relatively brief but intense GRB could have triggered the specific atmospheric changes observed in the geological record. According to their calculations, a gamma-ray burst lasting mere seconds could have initiated a cascade of chemical reactions in the atmosphere, depleting the ozone layer and allowing deadly UV radiation to penetrate to the surface. The researchers found that a GRB would have been particularly devastating to the ecosystems of the Permian period. The majority of life during this time was aquatic or lived near water surfaces, precisely the environments most vulnerable to increased UV radiation. Their atmospheric simulations show that the specific pattern of ozone depletion following a GRB would create extinction patterns consistent with what we observe in the end-Permian fossil record. Marine ecosystems, which suffered the most severe losses during the end-Permian extinction, would have been especially affected by the radiation aftermath of a GRB. Surface-dwelling marine organisms would have experienced direct DNA damage from increased UV radiation. This explains why certain groups like trilobites, which had dominated marine ecosystems for hundreds of millions of years, disappeared completely, while some deep-water organisms managed to survive. The terrestrial fossil record reveals that land animals with specific adaptations, burrowing behaviors, nocturnal lifestyles, or effective melanin production show higher survival rates than their counterparts lacking these traits. These adaptations would provide protection against increased surface radiation following ozone depletion, adding further weight to the cosmic radiation hypothesis. Geochemical evidence provides additional support for the GRB theory. Researchers have identified unique chemical signatures in end-Permian boundary layers that indicate sudden, intense radiation events. These signatures include isotopic anomalies and radiation-induced mineral alterations that are difficult to explain through volcanic processes alone. When mapped globally, these chemical markers show a pattern consistent with a planet-wide radiation event, a cosmic fingerprint left behind in ancient rocks. Scientists calculate the probability of a gamma-ray burst triggering the end-Permian extinction by combining astronomical data with Earth's geological record. They analyze the frequency of GRBs throughout the Milky Way, model Earth's position within the galaxy over geological time, and calculate the danger zone around potential GRB sources. This analysis determines how often Earth would have passed through these zones during its 4.5 billion year history. By factoring in the directional nature of GRBs, which emit energy in narrow beams rather than in all directions, scientists can estimate the probability of Earth being in the wrong place at the wrong time. The position of our solar system within the Milky Way influences our GRB risk. Earth's orbit takes us through different regions of the galaxy over hundreds of millions of years, sometimes bringing us closer to areas with higher concentrations of massive stars. Tracking these orbital cycles helps scientists identify periods when Earth would have faced elevated GRB exposure. When all these factors are combined, researchers can calculate probabilistic risk models. These models suggest that Earth has likely experienced at least one significant GRB impact during its biological history, with the end-Permian extinction representing a potential candidate based on the unique evidence preserved in its fossil record. The GRB hypothesis doesn't necessarily replace the volcanic explanation entirely. Many scientists now consider the possibility that the end-Permian extinction resulted from multiple coinciding catastrophes. A perfect storm scenario where volcanic activity and a cosmic radiation event combined to create particularly devastating conditions for life on Earth. The